All right, time for a discussion about patterns and trends in ionic radii. We talked about atomic radii before, and remember that the more shells an atom has, the larger the radius. But what happens when you take electrons and change them, adding in and losing them to become ions? Well, here's a chart from a text that shows the cations, the typical cations, and these are group 1 cations. And they are going to be always smaller than their corresponding neutral atom, simply because you've removed an outer shell electron. The size of the ion is always smaller than the atom from which it came. This is also related to the effective nuclear charge. In other words, the outer electrons are going to be a smaller number than the actual charge, and so the ratio of the charge to the electrons is greater, or the nuclear charge, the protons, and it pulls the electrons tighter, the ones that are present. This is group 1 elements in this diagram. Group 2 elements works in exactly the same fashion, so it's always going to become smaller as you lose electrons from that outer shell. Notice again, these are going to be group 2 elements losing 2 electrons, and they get quite a little bit smaller when they take off those 2 outer shell electrons. But think again, they are going to have an effective based on the effective nuclear charge. In other words, beryllium has a nuclear charge of 4 and 4 protons pulling on 4 electrons in a neutral atom. But in the case of beryllium as an ion, it's only got 2 electrons to pull against instead of the 4 electrons. And 4 electrons here are not pulled as tightly as 2 electrons in the inner shell that are remaining, the 1s shell. Same pattern applies to each of the other alkaline earth metals. These are good patterns to recognize for cations. They're always going to get smaller. Now, what about anions? Well, anions are from the nonmetals, and the anions, as you can see from this diagram, are going to be larger than their corresponding neutral atoms because you're getting an extra electron in that outer shell, and it increases the number of electron repulsions and decreases the amount of effective charge of the protons against the outer shell electrons. And so you add an electron to the outer shell, it will increase each time. The actual numbers here are not the issue. We want to see the patterns. So every halogen shown here has a larger ion than its corresponding atom. So using that information, we can kind of make some interesting comparisons even without having actual numbers not knowing the actual numbers, we can figure them out. So we've got some values here and some pictures of lovely spheres, and we're trying to decide which ones are which. So we'll have to decide what patterns might be. Thinking back to the sizes of atoms, yes, atoms are largest on the metal side and smallest on the nonmetal side. And so if you have to decide between the potassium ion and the potassium atom, the ion is going to be smaller than the potassium ion. Oh, sorry. The atom will be larger than the ion, and the chloride ion should be even a larger ion yet. Think this one through now. The chloride ion is going to be what compared to the other two? So you have to think about what row in the periodic table we're looking at. And potassium is going to come down to an ion that's isoelectronic with its nearest neighbor, argon. And potassium atoms will be bigger than the potassium ions. But the chloride ion will also be isoelectronic with argon. And so it will become 18 electrons. Now, which one is going to be larger, the chloride ion or the potassium ion? Well, chloride will be the largest because it has gained electrons and become larger, and nonmetals, with adding on an electron to become an ion, become large. So the chloride is going to be that one. The potassium ion has to be the smallest one, and this in-between sized one will be the potassium atom. All right, now here's some interesting patterns that help to make sense of the whole scheme of how the radii and ions of familiar elements look. And we can look at potassium and chloride ions here and see that potassium is in fact shown here with 133 as its radius, potassium ion, and the chloride ion as 181. If we go back to the previous slide, well, it's close. The radius is not exactly the same for this set of data. But let's think about the patterns. So notice that if we have isoelectronic cations, the tri-positive ions, in other words, +3 ions, are going to have smaller radius than those with a 2 or single plus charge. And so isoelectronic ones, well, what are we thinking of? Let's look at this. So isoelectronic would be like aluminum with magnesium and sodium. The one that's tri-positive, namely aluminum, is going to be the smallest because it's got more protons pulling on the same number of electrons, namely 10 in this case. The same pattern works for gallium and its neighbors, calcium and potassium. So the tri-positive ones are going to be smaller. Notice, however, in a general sense, the way with the atoms, they get larger as you go down a period, and they're going to get smaller going across, or get larger going away from the noble gases. Now let's look at some more patterns. For anions, the radius increases with the number of negative charges. So the more negative charges you have, which is what I was just pointing out on the previous page, the negative charges, the more there are, the more diffuse they are around a smaller number of protons, and they get larger. So fluoride, oxide, and nitride ions are going to be increasing in size, with the one with the triple negative charge being the largest. Same pattern applies to the ones in the subsequent rows, but their differences are not as profound. Look at the last row. Not quite a foolproof comparison. Notice also that there's charges shown for two types of iron atoms, and the smaller of the two iron ions, and the smaller of the two will be the iron 2, and copper 2 is likewise smaller than copper 1. So the larger the charge, the smaller the radius for these ions. All right, so let's think about these types of examples and see if we can sort it out. What's going to be the largest, medium, and smaller of each of these? So we got 4 different sizes and 4 different ions, and we have to place them in the periodic table in our minds a little bit and remember where the largest ones and smallest ones are. The smaller ones are going to be the cations, and so we're expecting those to be either 2 or 4, so let's put a plus sign for the cations there. And the smaller one is the one with the smaller, either with a larger charge or fewer shells. Well, in this case, magnesium and sodium are both going to have an outer shell that comes down to a neon configuration. Then that would be the 10 electron thing. So the one with the higher number of charge, the doubly positive charge, is going to be smaller than the one that's single plus. And so magnesium better be the smaller of the two, which looks like number 4. So let's put magnesium here. And magnesium plus 2, of course. And the sodium, which should be the other small one. Then the larger ones, the larger spheres, are going to be the anions. And the anions, they're going to vary either with the number of the negative charge or with the number of shells. Well, in this case, we got both possibilities because the fluoride ion is in the second period and the sulfide ion is in the third period. So the sulfide ion better be the largest. And so the largest one should be sulfide because it's got one more shell of electrons, and the fluoride ion should be not as large. So let's look at the pattern here again. So the largest is going to be the sulfide ion with more shells. Third shell is full. The smallest one would be the magnesium ion because of the +2 charge, and it's a neon configuration with 10 electrons. The second largest is the fluoride ion, and the second smallest is the sodium ion. See if those patterns make some sense to you. All right. Enough said about atomic radii for the day for now. Misstated ionic radii. That way. Good luck working on your examples.